In this video, we will learn briefly about what nuclear magnetic resonance or NMR spectroscopy is, so what the working principle behind NMR spectroscopy is, what typical NMR data looks like, and some of the features of the data. So the way NMR works is that it takes advantage of the fact that if you put nuclei in a large external magnetic field, they will have differing energies depending on whether their nuclear spins are pointed with the magnetic field or pointed against the magnetic field. For the purposes of this class, we will think just about m equals 1/2 nuclei, so spin 1/2 nuclei. These are the most common elements that you'll see in organic molecules, so hydrogen, carbon, nitrogen, fluorine, phosphorus. Take note that these are for specific isotopes. For example, carbon-13 has spin 1/2, but carbon-12 does not. In terms of what we're looking at, well, so here is a nucleus and its spin direction. So if a nucleus is just in a normal situation with no external magnetic field, then it doesn't really matter which way that spin is pointing. The nucleus will always have roughly the same energy. Putting that nucleus into a large magnetic field, however, causes a difference in energy based on the direction of that spin. So if the spin is aligned with that external magnetic field, it tends to be lower in energy, and if the spin is opposed to that external magnetic field, that's higher in energy. The delta E here is the energy gap between those two states. That's related to the energy of absorption that's detected by the NMR instrument. It turns out this delta E is incredibly small, small enough to the point that to even be able to observe any of this delta E, we need to use very large external magnetic fields to separate these two states from each other energy-wise. The reason this happens is because of this mathematical relationship where the delta E is equal to the magnetic moment, mu, over the spin of the nucleus times overall the external magnetic field. So this is the value that we're increasing to try to get these energies to differ more. A typical external magnet for NMR will range between 1 and 20 Tesla. To give you a sense of scale, a magnetic resonance imaging instrument, or MRI instrument, that you would find at a hospital for imaging the human body, that operates on the same principle as NMR, and the typical hospital version will be at 1.4 Tesla. These energies correspond to extremely small values if we're thinking in calories per mole, so the difference in energy here is related to a delta E that's less than 0.1 calories per mole. So just to calibrate yourself, if you think about a hydrogen bond being 1 to 3 or maybe a little bit more kilocalories per mole and a carbon-carbon bond being closer to 100 kilocalories per mole, this is many orders of magnitude lower in energy, so very small delta E. Because we're working with radio waves, people like to think in terms of megahertz and their frequencies, and so these delta E's are related to a frequency of 20 to 900 megahertz. And so what we'll say is that the NMR instrument is operating at 900 megahertz, for example. So then in the experiment, what we're really doing is we're trying to identify places where the nuclei are absorbing energy, and when that happens, we call that resonance. So the way the instrument works is we take the external magnetic field and we can vary that little bit by little bit, and as this B naught value here changes, that changes the energy gap between the two different spin states right here. So our instrument is sending out a constant frequency, so then we can find the various external fields at which the nuclei absorb energy. A slightly closer look at the process is like this. So nuclei are actually excited to the higher state by radio waves, and we can watch them kind of relax back down. That helps us figure out what this delta E value is. The workings of NMR are much more complicated than just looking for a spin up and a spin down. In the details of it, we're looking at what are called precession frequencies. So precession is the process in which I draw the spin kind of at an angle like so, but really it's also rotating this way. So this process is called precession, and those frequencies can be detected and kind of summed up as a single electric signal in the NMR instrument. And then whenever you have an electric signal that is composed of a lot of different other signals added up together, we can perform a technique called Fourier transform. So this is a lot of math, but with Fourier transform you can take that single signal that's detected and kind of deconvolute it and extract out the individual frequencies that had summed up to the overall signal. So here I'd like to show you what an NMR instrument actually looks like. So this is the Macalester College NMR instrument. It's a 400 megahertz NMR. if you're looking at this white tank-like object here, this is the white part is the shield, and inside this shield is the strong magnet. So the reason we need a shield is because if this magnet was just exposed to the outside, everything metal in the room would just get sucked into that magnet, and then the magnet would break. The samples are all kind of put in by a robotic system into the inside of this shield, inside this magnet. And then around this magnet are some coils, and those coils generate some frequencies through these wires underneath here, which are connected to this white box in the back. So this white box is actually where the radio frequencies are kind of measured and detected. And of course we have our computer here to run everything. To give you a sense of cost for one of these, it costs about $20,000 a year to maintain the instrument and keep it running. And then to buy one of these instruments, the going price is somewhere around $100,000 per 100 megahertz. Not totally linear, because if you own one of the few 1000 megahertz instruments in the world, then you're paying well over $1 million. Okay, back to actual NMR data. So in NMR data, what we are going to be looking at are signals, which are also called resonances. And these signals or resonances will appear at different chemical shifts. And these chemical shifts, which is what's on the x-axis, will depend on the environment of that nucleus in the actual molecule itself. So a lot of pieces there. Let me give you an example of some data. So this is what's called a proton NMR. When we talk about NMR, we'll say proton frequently instead of hydrogen. The reason is that a hydrogen atom is going to have just a proton as its nucleus, so for whatever reason people have just started to say proton when talking about proton NMR. So this is the NMR of the molecule right here. This data is relatively simple when it comes to NMR, but there's still a lot to point out. So let's start off thinking about the x-axis. So the x-axis is presented to you in this unit, what's called ppm, with a delta next to it. So ppm here stands for parts per million, and what this is reflecting is that this is the deviation away from kind of the standard megahertz, which the nucleus is supposed to be absorbing energy. And so we set that standard to be 0. So this is a little bit arbitrary, but we kind of have a convention for where the 0 is located, so it's always here. And then relative to the 0, we can measure the number of ppm away from 0 that we are. And so what that tells us is that if we are 4 ppm away from 0, we are 4 millionths less delta E than the 400 megahertz of the instrument, for example. So that means that the signal here is coming in at 399.9996 megahertz. So really NMR spectroscopy is detecting very tiny differences in the chemical environments of nuclei in the grand scheme of a molecule. If you're looking at this data, some of our signals are a little bit more complex. So some of them show up as kind of a single peak, which you might be more used to from IR, for example. But some other signals show up as what seem to be more complicated patterns. For example, here this is called a quartet, and this is called a triplet. The reason there are all these patterns is because the various nuclei within a molecule can also interact with each other, leading to slightly different delta E's for various different nuclei. And so this so-called splitting pattern is very useful for giving us a little bit of information about the nuclei here and its neighbors. So HB is labeled here. This signal actually tells me that there's 3 other hydrogens close by to this one. Finally, if you're looking at this molecule, you'll notice that there are a total of 8 hydrogens in the molecule, but we only see 3 signals overall in the data. And so the reason for that is because when nuclei have the exact same chemical environment within a molecule and the exact same splitting pattern and everything, then really what we're saying is that each of those nuclei is going to have a signal at the exact same x-axis location. And so the symmetry of the molecule then becomes very important, because if molecules are symmetric, then a lot of its nuclei will be the same just by kind of rotation of a molecule, which means that those nuclei are in the same chemical environments, which means the NMR sees them as being identical. If you look out here at the CH3 group, these 3 hydrogens are going to be the same, so they all show up at the single peak right here. All right, so that was a brief look at how NMR works and what the data looks like and some of the features of that data.